thank you very much for inviting me to this nice conference. Yeah, first of all, it just turned out that writing on this screen, which I thought would be a good option, would irrevocably terminate the full screen mode. So I just have to go through the transparencies, and let's see. So yeah, the topic is metrizations in Lorentzian geometry, and there's actually it splits into two topics. First of all, I want to revise some metrizable topology on the future completion, which is the set of indecomposable path subsets of a space-time, say, and compare it with the usual chronological topology. And the second topic is just it's a bit more recent. It's a functor from a category of Lorentzian manifolds to a category of Riemannian manifolds, and maybe some applications towards finiteness theorems in Lorentzian geometry. So I mean the common denominator is metrizations. And metrics in the world of Lorentzian geometry, and of course metrics are a bit remote from Lorentzian metrics. So metric spaces are a bit remote, and there is a reason for that. We will come to this in a minute. First of all, I want to begin with a quote by Marcel Berger in his nice book Panoramic View of Riemannian Geometry. He says there, Gromov MM spaces, these metric measure spaces, are, in our opinion, the geometry of the future. It's really the quotation as it is there. So being a Lorentzian geometer, so this emoji represents a Lorentzian geometer, confronted with this quote, and actually confronted with this quote, being a Lorentzian geometer, you have two possibilities. You could sit down in a corner, sullen and stubborn, and say, well, we don't want to have to do anything with metrics and metric measure spaces and Gromov's program. This is the first possibility. The second possibility is to try to get an invitation to the party and so be part of the game. And I think, well, at least for the time being, let's pursue this second approach, because I mean, if we are honest, this program of Gromov's has been very fruitful in Riemannian geometry. So, for example, so understanding Riemannian metrics as some particular instances of metric spaces, and in a sense widening the scope, has been very fruitful. For example, for the finiteness theorems, like you consider some subset of metric spaces. You show that it is compact in the Gromov-Hausdorff metric, and then in the end you show paramount stability, or not in the end, but historically. But you use paramount stability, meaning that if you approach a limit, then and it is then you show that it's a manifold, and the diffeomorphism type does not change in the end. And the question is whether Lorentzian geometry could be participate in this party, in this industry, so to say. We'll see that this is indeed possible. But there's a drawback. I mean, there's some simple fact that could discourage you. This is actually this is probably known to everyone who has thought a bit more about Lorentzian geometry, that there is no functor bringing you from Lorentzian manifolds to metric spaces, and at the same time leaving the topology unchanged. This is not possible, and the reason is just that, for example, if you consider boosts in Minkowski space, they would accumulate at the zero vector. They would dive arbitrarily deep into every neighborhood at 0. So this prevents us from getting any functor from Lorentzian from a category of Lorentzian manifolds from the category of Lorentzian manifolds to metric spaces. But we'll see in the end how to get a loophole around this this fact, in a sense. Okay, but first of all, let's consider metric approaches in the future completion. Let's just revise shortly what the future completion is. So if we have a space-time, or say a chronological space, which is a slight generalization of space-time, a bit in the spirit of generalizing Riemannian manifolds to metric spaces, we consider the set of indecomposable past sets. That means, well, past sets which are such that they cannot be written in as a union of any two non-trivial past subsets of them. So, well, a well-known fact is then that if we have an indecomposable past set, then either it is the past of a point of space-time, for example, or it is the past of the image of a curve, which is time-like future and continuously inextendable. And then you can, well, you can put some natural chronological relation on the space, and this is like that you have, if you have two subsets A and B, that then you say A is in the time-like past of B, if and only if the joint future of A, this means the intersection of the futures of every point of A has a non-trivial intersection with B. And the causal relation is just given by the subset relation. Yeah, if you apply those definitions, then you can do some causality theory on your future completion. And then you have a canonical injection which preserves all those causal relations and chronological relations, which is just mapping a point to its past. Yeah, then the question is which topology to put on IPX. And this has been the subject of a very extensive debate. And there is an answer to this question, which is quite reasonable because it's very widely applicable. You just define the topology tau minus as the subset of the complements of those sets. So, like now we define the closed sets. The closed sets are those sets such that if we have a sequence in those sets, A, then the limit operator L minus is again a subset of C, and L minus of A is just the set of indecomposable past subsets, non-empty, such that well, they are contained in the set theoretic lim-inf of the sequence, and they are maximal in the lim-sub of the sequence, in the lim superior. So this, as I said, this topology is very generally applicable. I mean, we have only to suppose that our space-time is strongly causal. We can apply it, and we get that the canonical injection is a homomorphism onto its image, and the image is dense in the future completion. So everything works out nice. A point I forgot, which is also quite important. Forgot to write it down here. Is that you can apply the whole thing to the entire completion, like the future and the past completion, and yeah, there you have some identifications between future and past subsets and so on, and everything works out well. The drawback of this topology is that it is non-Hausdorff and let alone metric. So it's not Hausdorff even for global hyperbolic spacetimes, and there is this famous example of the Lorentzian line of the product of the Lorentzian line with the unwrapped grapefruit on a stick created by Stacey Harris, so this is even for global hyperbolic spacetimes. It's not a metric topology in general. So this is a certain drawback depending on your taste of topological spaces. So there is another option, and the history is quite interesting because I in a paper of 2016, it appeared 2016. I just used it to show something about the conformal boundary, and I gave a very sketchy proof of proofs regarding this topology, and then after some years. So I thought this was a nice discovery, and then after some years, a group like Ivan Costa y Silva, José Luis Flores, and Jonathan Herrera, they examined very precisely this metric, very meticulously, but then it turned out. Looking at this, at the context a bit more specifically, we noticed that this metric had been discovered already by by John Beam in 1977, he had already seen that you could apply to every causally continuous spacetime, which is more specific than strongly causal, and that this canonical inclusion is a homomorphism onto its image, and the image is dense. This definition of this topology is the following: you take a limit operator as above, but here you consider only those subsets such that the pasts of the subsets, the past of the lim_inf of the sequence, and the past of lim_sup of the sequence is just the past of the corresponding set. So this is just a definition of a limit operator, and it's quite abstract, but it can be made very concrete by considering a metric. And this is the following one. A look at the third point here. This topology is actually metrizable. It's if you apply to if you put a volume form on the manifold, meaning a top form of mass 1, then you can just consider the volume of the symmetric differences of the sets, right? I mean, you have two subsets. You consider its symmetric difference, their symmetric difference, and then you consider its volume, and that's the metric. Very easy definition. But it turns out that this metric is less generally applicable because you can only apply it to causally continuous spacetimes, which is a bit higher in the causal layer. So you see easily that for every spacetime, the metric tau minus, the topology tau minus is contained in the topology tau plus. So topology plus is finer, which you would expect of a, let's say, Hausdorff metric, maybe Hausdorff topology, and then also, as I said, in 2016, I used this just to look for obstructions to the existence of a future conformal compactification, because if there is one, it has to coincide topology with this abstract future boundary in IPX. And then also, Costa y Silva, Flores, and Herrera in 2019 proved that if the topology tau minus is Hausdorff, then it coincides with tau plus. You can also see that if tau minus is causally simple and future compact, then it coincides with tau plus. And you can compute tau plus in several examples, like multiply warp spacetimes. There's a very nice previous corresponding work on tau minus by Stacey Harris, you can just transfer the results to multiple warp spacetimes about multiply warped spacetimes to tau plus. Okay, now for the loophole I promised you, which could bring us to Gromov's program. So the question is whether we could maybe restrict the Lorentzian category to finally get a functor to metric spaces, and the answer is yes. So it's an article on the archive of from 2019, but I would like to ask you to not to look it up right now, because I correct some mistakes, and it's merely a question of days, I think. So at the latest next weekend, there will be a new version, I just want to prevent you from stumbling upon several mistakes in the previous version. This is mainly okay. So you have the category C, which is formed by the C infinity, the smooth Cauchy slabs, which means just they are Lorentzian manifolds with boundary. They are just regions between two Cauchy surfaces for a global hyperbolic spacetime, right? So they have two boundary components, and they are Cauchy surfaces. And the morphisms we want to admit are isometric and oriented and time-oriented diffeomorphisms. Yeah. Okay, and the Riemannian category in the game is the one of smooth Riemannian manifolds, boundary, and isometries. Now, if you consider any, let's say, a function from R to R, which is measurable and locally essentially bounded, we can consider the following thing. We just consider every point x in our spacetime, we could map to the signed Lorentzian distance to x, meaning it's positive in the future, negative in the past, and we compose it with f. Like we want to have some liberty of composing it with some function. And then the idea is just okay. So our target is LP of x, which is a Hilbert space, right? So the point is, we could just pull back the extrinsic or intrinsic metrics from the Banach spaces. Well, LP or L2 is a Hilbert space, and LP is a Banach space. So we could pull back the metrics, meaning distances, or the infinitesimal metrics from the Banach spaces on the right-hand side. I mean, it's a very, very basic idea. It's not, well, yeah, but not anything special. But the interesting thing is that it actually works. So if you why does it work? Because you restrict yourself to Cauchy slabs, such that all the volume forms you use are of finite volume. I mean, if you have a Cauchy slab, then you are future compact and past compact. So all your future cones are compact and past cones are compact. So this works, and it circumvents, so to say, the drawback mentioned before. So if you consider the characteristic function of the negatives, and you put p to the to 1, then you get the B metric before. This is the link to the first topic of this talk. But okay, this is somehow for our purposes. I mean, we have finiteness theorems just in our mind as the ultimate goal of this business, or an important goal. And the B metric has splitting geodesics, which does not happen for any Alexandrov space. So this Perelman stability holds for Alexandrov spaces, and Alexandrov spaces do not have splitting geodesics. So okay, this means, I mean, the B metric here refers to pull back the distance of the Banach space L1 of x by the extrinsic distance by this map and phi f, yeah, and therefore if this distance already has splitting geodesics, then the well, the infinitesimal version as being the metric, the corresponding length metric, has also splitting geodesics. So this is somehow a dead end. But our choice now is just we go to the Hilbert space. We use a certain combination of the identity and sign function, convex combination, and the square function, right? And then for every parameter r, we can prove that this is actually a smooth embedding into the Hilbert space. We can even write down the derivative in a very nice way. And then it turns out that this functor bringing us from the Lorentzian side to the Riemannian side is an injective functor into a category of isometry classes of Riemannian objects on the right-hand side with 3 Lipschitz functions. So this is, due to technical reasons, I have to just add 3 functions and to interpolate between them to get the entire metric back. But I think it's a technical assumption. I don't think this is really essential here, but this is also a work in progress. Yeah, then we can just write down the derivative, and this derivative is just if you remember that the Lorentzian cut locus is of full measure. I mean, the future cut locus is of full measure in the future cone. So if you just assume that so you have a point x, yeah, and you have a vector v in txm or txx, and you want to know the derivative of f g f0. Then what you do is that you go to the point x of w, which is in the future or in the past of the point. You assume that it's not in the cut locus. That means there is a unique maximal geodesic from x to x of w, and then you take this w and then you take the scalar product. So this is the derivative of our map. It's a function, yeah. And it with a support in the future in the causal cone. And you can also write down the Hessian, and here you get basically the same thing. Here also the W has the same meaning, and you have just the scalar product between V and the Jacobi vector field, which begins with a V and ends up with this should be a 0, not a 1 here. Okay, so this kV of 1 should be 0, of course. Yeah, ends up with a 0. And if you do this, you get actually finiteness statements. I mean, we can define some quantity gamma of x, which is just basically a combination of volume and future injectivity radius. And then you have the statement that if we fix the dimension and we assume some bounds A3 and A4 on the time-like diameter and on the volume, then we find some bounds on the time-like sectional curvature and the second fundamental form of the boundary, such that for all bounds on lower bounds on this quantity gamma, we have only finitely many homomorphism types. This is not a very strong finiteness statement, but still, I think it's the first one in Lorentzian geometry, the first genuinely Lorentzian finiteness statement. So maybe it's interesting, and I think it's somehow a flexible machinery, because you can put in a function f, and for example, you can interpolate between the B metric and some earlier program by Johann Noldus, some Noldus metric. And I think it's interesting to play around with this machinery. And yeah, so we got a functor from Lorentzian subcategory to a Riemannian category. Yeah, maybe it's interesting to see how this connects to different concepts of metrization in Lorentzian geometry. Yeah, I think this is everything I had to say.